from Friday we went outside and we made waves. Hopefully you raised it to the same height, right? If you raised it to the same height, what value should have been the same in your data chart? Which one? Amplitude, right? So take a look at your data. How close are your amplitudes? Are they fairly close or not at all? Right? So looking at that data, the amplitude shouldn't have changed. Okay? Amplitude shouldn't have changed. Now, looking at your normal pace, fast pace, slow pace, check your times. Your fast pace should have the smallest amount of time. Slow pace, greatest amount of time. Yes? Okay. Now, wavelength. When I walk slower, when you guys walked slower, did you have more waves or less waves? When you walked slower, there's actually more waves that were produced on the ground. So hopefully if you look in your data chart, the slower pace should have the most number of waves in 4 meters. So that means that it was more or less frequent? More frequent. If it is more frequent, does that mean the wavelength is longer or shorter? Shorter. Good. All right, so double check your data. Does that support it? Is your wavelength the shortest for the slow pace and the longest for your fast pace? Hopefully that's what your data should have saw, okay? And then you guys had calculated frequency. Again, units for frequency are Hz, which stands for what? Hertz, right? Hertz. When you calculated frequency, what you guys just told me is that my slower pace had the highest frequency. Is that what you found? Yes? Yes? Okay, that's good. That's good. All right. Then when you went on to the second page, take a look at your second page. Your calculations. Each way that you calculated it, we could have done it a traditional calculation like when we were solving for motion back in January and take distance divided by time, right? That will work for any type of object. But maybe we don't know what distance the light is actually covering, right? So instead, we might understand frequency and wavelength a little bit better. So we could have calculated it by taking wave speed equals frequency times wavelength. Did your values end up pretty close to each other for each trial? Yes, they should have. They should have, hopefully. Bless you. Okay? All right, now let's take a peek at those questions. So number 1, compare the speeds calculated in the previous 2 steps. Are they the same? Answer should be yes, they should be. No matter what, even if we calculate it a different way, the speed is the same, right? Even if we use a different equation, we should still be getting the same results. Number 2, when frequency goes up, wavelength goes down. So remember, those ones are opposites of each other. So if I increase the frequency, the waves get closer together, so the wavelength is less. Okay? All right, number 3. Did the wavelength change after walking at a slower pace? Yeah, because that changed the frequency, correct? All right, 4. Did the amplitude change when the pace changed? You might have to say yes because your data says yes. But number 4, should our amplitude have changed? No, not at all. It shouldn't. Okay. All right, 5. It says blue light has a higher frequency than red light. Does blue light travel faster than red light in the same medium? Who says yes? Show of hands. Okay, who says no? Show of hands. All right, why are my no's saying no? All right, they are part of the same electromagnetic spectrum, right? They are part of white light coming from the sun, traveling through a vacuum. Remember, they travel at the speed of light. That's 3 times 10 to the 8th. Okay? So question for you. Just because they have different frequencies, okay? So if they have different frequencies, and we calculate speed, so our wave speed, they do it with a fancy V, is frequency times wavelength. Well, if I increase the frequency, what happens to the wavelength? It goes down, right? So won't those counteract and cancel each other out? So even if they have different frequencies, can they travel at the same speed? Yeah, okay? Because they are electromagnetic waves. So if you look, number five, does blue travel faster than red? No. No, because when we are looking at that calculation and we are going and we are saying that wave speed equals frequency times wavelength, if the frequency goes up, wavelength goes down, and they kind of cancel each other out. Okay? So the speed, if you're in the same medium, is always going to be 3 times 10 to the 8th, which is our speed of light. Okay? All right, what did you say for 6? What would you have to do in order to change the amplitude of the wave? Increase the height, right? We said water waves, the taller it is, the more or less energy it has. More, right? So if I raise the cup higher, I'm giving it more, what kind of energy? Potential. Nice. Look at you guys. Boom. All right, so if you have not submitted this yet, go ahead, take a quick second, shoot that into Canvas so you don't have to worry about it. So go ahead and hit submit. And then what I want to do a quick debrief. I have a couple slides to go over with you in terms of wave speed. So this is what we should have gained from our lab, hopefully what we gained.
I feel like that was directed at our table.
No, not at all. Not at all. It's what I think you should have gained, right? It's not necessarily always what you gain, but hopefully maybe. All right, so reminder, we have frequency, wavelength, wave speed, and period. These are some of the new key terms that we are introducing for you guys. Frequency is abbreviated with an F. That is the symbol, but its units are hertz. Good. Wavelength, upside down Y is what we introduced it as, but it's technically called, so it's an L.
You did not. There's no way you told us.
Totally did. Lambda.
No.
Lambda.
I don't remember that.
For sure. Okay. So wavelength is lambda, but our units would be something of a length measurement, like meters, not inches, not feet, meters, centimeters, nanometers, things like that. Wave speed is that V, or a fancy V. You can see it abbreviated different ways. Meters per second. And then we said period, capital T, is a measurement of time. It is how long it takes for one wave to pass. So if I said how long is our period for this class, you would say 48 minutes, right? So when we look at those things, those are going to be some of the different calculations, guys, that are going to pop up in our calculations as we start moving throughout the week. Okay? All right, so question for you. All right, as the wavelength of a wave in a uniform medium increases, what happens to speed? Who says A, decrease? B, increase?
Oh, wait.
C, remain the same.
Wait, hold on. Give me a moment.
All right, give a moment to think about it. So as the wavelength in a wave increases, what's going to happen to my speed? Okay, here I'll give you a reminder. Your equation was wave speed equals frequency times wavelength, if that helps you out. Okay, all right, so I'm going to increase the wavelength. Who says A? That's going to cause a decrease in the speed. B, increase in the speed. C, stay the same. Come on, stay the same. So raise your hands higher. Yes, you got it.
I don't know what I'm doing.
Got it. Because, hey, what did we just say? Speed of light is always going to be 3 times 10 to the 8th.
Okay.
Because if I increase the wavelength, my frequency goes down, remember? So they're going to counteract. They're going to be opposites of each other.
Nothing about frequency in that equation.
It doesn't matter. If you increase the wavelength, what happens to your frequency? Right? All right, next one. As the wavelength increases, what happens to frequency? As wavelength goes up, what happens to frequency?
It goes down.
Frequency goes down. Yes, good job. So frequency is going to go down. All right, number 3. The speed of a wave depends on, take a look at your answer choices. A, properties of the medium in which the wave travels. B, wavelength. C, frequency. Or D, wavelength and frequency of the wave.
D. I don't know.
A?
All right, who's going A?
A.
B? C? D? All right, so
D is the equation.
D is the equation.
But.
But it's wrong.
But,
Oh, God. Wait. What is
but,
wrong?
won't the speed of light always be 3 times 10 to the 8th power?
Yeah.
Yes.
What is going on?
Now, when will light, hey, answer me this. We had mentioned this on Friday. When will light slow down some?
No, because if wavelength.
I don't know.
When it travels through our atmosphere or travels through the water. Do you remember my vibrating cell phone, holding it in the air versus setting it on the desk? When does it sound louder?
Girl.
On the desk? No, I give it as an example. I didn't actually do it in real life. I actually do it in real life,
I
right?
can't do this today.
All right, so speed of the wave depends upon the medium. So here's your key note. Key note.
I thought
Okay.
it depended on the equation.
Well, because they cancel each other out. That's how I can calculate it, but the frequency actually won't impact it. So
Wait, so what was the answer?
A. So take a look, guys. So wave speed, I know they're in the equation, but those are just independent properties of it. Like red has a longer wavelength than blue, okay? That just is, okay? That's not going to change the speed though, because the speed is always going to be the same. So the wave speed is not affected by wave properties such as frequency, wavelength, amplitude, okay? Speed is dependent or is changed if I use different things. I move it through a different medium. I change the tension in a spring, or I change the density of the particles that the sound travels through, right? So if I had a vibrating cell phone right now and I was holding it in the air, it wouldn't sound super loud. But if I set it on that desk, it's gonna sound louder, right? Because the particles are denser in a solid than they are in the air, right? So when we look at wave speed is only going to be affected by the medium of which it's traveling through. Light will slow down as it goes from a vacuum into our atmosphere. And as it passes through water, it slows down even more, okay? So check out this one. Check out a little small for you guys, but at the top it says 1. A teacher attaches a slinky to a wall and begins introducing pulses with different amplitudes. So if you see wave A has a bigger amplitude, wave B has a smaller one. Which of the pulses will travel from the hand to the wall in the least amount of time?
A.
Who says A? B. How about they get there at the same time?
Oh, yeah.
Ah, they get there at the same time! Because does amplitude affect my speed? No. All right, take a look at number 2. The teacher then begins introducing pulses with different wavelengths. which would actually reach the wall in the least amount of time? Who says wave C, which is the first one? Wave D?
No.
They get there at the same time?
Yes, ma'am.
Aha, we finally got it. They get there at the same time. They get there at the same time. So, this one, I know it's remember, waves will travel at different speeds. Okay? Waves will travel at different speeds when they move through different mediums. Okay? For an electromagnetic wave, like light or UV, electromagnetic waves can travel through a vacuum. They can travel out in space. So that's actually where they're going to travel the fastest. So electromagnetic waves do not need a medium. Okay? So they do not need a medium. So when they do end up moving through mediums and it becomes denser, it's harder for them to travel as fast. Okay? Whereas a mechanical wave, like sound, vibrations, things like that, as you increase the density, so holding the phone in the air versus setting it on a solid desk is going to sound louder. The wave increases its speed because mechanical waves do require a medium. M mechanical, M medium. Mechanical waves require a medium. Okay? So mechanical waves do want mediums. So if you make it more dense, that's better for them. They travel faster. Electromagnetic waves do not. Okay? They don't need a medium. They don't need a medium. So they aren't going to travel as fast in something that is denser. Okay? All right, so do you have the relationships down pat now? All right, if I increase frequency, what happens to wavelength? It decreases, good. Okay, so that one, it decreases. If I decrease frequency, I increase my wavelength, good. If I increase amplitude, so I just make it taller, is that going to change my wavelength? No, so that's going to have no effect. Good. What about if I increase wavelength? What's going to have on my speed?
Nothing. It doesn't do anything.
Yes! No effect.
I got that one.
Y'all try.
Okay? Because if I increase the wavelength, that decreases my frequency and they counteract each other. Okay? I still am going to calculate the same wave
That only
speed.
happens if you have a set speed, though, right? Like, what if you don't know the speed at all and you increase the... Do you know what I mean?
I guess, but no matter what, if you increase one, you're going to decrease the other. So if I increase this by tenfold, this goes down by tenfold.
Like, why?
So then it cancels out. Because they're connected, right? Because if I do make it more frequent, the wavelength does get shorter, right? And that's just a physical phenomenon. That's what happens with the waves. They get closer together or stretching it out, okay?
I did get a 30.
All right, check that last one then. Increased frequency, what happens to my wave speed? Nothing, no effect, no effect.